Hello, Mr. Betts here. We've already looked at how we can take the derivative of the arcsine function and the arctangent function, so now I'm going to do the same thing with the arcsecant function. And the idea is going to be the same. I'll start with writing y equals arcsecant of x. And so our goal here is to find dy dx. So essentially, this is just saying I want to take the derivative of y, but I'm replacing y with arcsecant. So it looks like this. So it's just a different way of writing this problem, but by including the by writing y equals here, then we can do some manipulation that allows us to do the problem. So the first thing we do is we take this equation and we take the secant of both sides. So the secant of y is equal to x. We take the derivative of both sides of that with respect to x. So the derivative of secant is secant times tangent. We keep the y in there. So secant times tangent. So we're doing implicit differentiation here. That inner function of y means we have to multiply by the derivative of the inner function, and then the derivative of x is 1. So we solve for dy dx, and we get 1 over the secant of y times the tangent of y. Now, right off the bat, the secant of y, we know what that is because that's right here. Secant of y equals x, so that's just going to be x. In the picture that I draw, though, I'm going to refine that a little bit. So I'm going to draw a triangle just like I've done in other ones. I'm going to use this equation right here to draw a picture of what the triangle looks like. So again, the angle is going to be y. Remember, secant is hypotenuse over adjacent because it's the inverse of cosine. So thinking of this as x over 1, hypotenuse is going to be x, adjacent is going to be 1. Pythagorean theorem gives us this is square root of x squared minus 1. Okay, so now I want to replace, and I didn't finish writing this out here. This should be a tangent of y here. I want to replace the secant of y and the tangent of y, so this is written in terms of just x. So the secant of y, remember secant of y is secant is hypotenuse over adjacent. Now in this triangle here, x is going to have to be a positive number. X doesn't necessarily have to be positive depending on how we restrict domain and range. If you remember how we did that, though, it turns out that the y values are all going to be positive in the secant function. That's not really that important, but what is important is the hypotenuse has to be positive. So whatever x is, the secant of y is going to be absolute value of x. Then the tangent of y, tangent is opposite over adjacent. So the tangent of y here is going to be opposite, which is square root of x squared minus 1 over 1. And we have the 1 in the numerator, and that gives us this expression here. If I were to ask you on an assessment to derive this formula like this, I'm not too worried about that absolute value part. I will say that we can plug in negative values for secant, but when we do that, we're going to get positive slopes for the tangent lines. So I might restrict the domain on the secant function to just positive x values so that we can handle that. So we end up with this expression right here, which proves our formula.